Hi, my name is Catherine Boerckel.
And my name is Allison Grove.
We are sophomores at Washington Liberty High School in Arlington, Virginia.
We thank you for your time and present to you our study, The Effect of Correspondence Between Strains of Prevalent Influenza and Strains Included in the Vaccine on the Effectiveness of the Flu Vaccine in 10 flu seasons from 2010 to 2020.
We became interested in vaccine creation as the rapid development of the COVID-19 vaccine has been crucial to pandemic relief.
With new variants of COVID consistently arising, we became curious as to how influenza is controlled while also facing constant emergence of new variants, and how exactly do scientists formulate the annual flu vaccine to accommodate new variant strains of the flu?
In considering the vast number of influenza strains circulating the population, how much does the effect of correspondence between prevalent strains infecting the population and vaccine strains have on the potency of the annual flu vaccine?
Because of the inconsistent prevalence of strains, the influenza vaccine's effectiveness varies from season to season.
Our background research also introduced the use of antigenic characterization, a process that is able to indicate the flu vaccine's ability to produce an immune response against the commonly circulating flu viruses, and hemagglutinin inhibition assay, or HI test, which allows scientists to compare antigenic properties between previously and currently circulating influenza strains to help select the candidate vaccine viruses. Both of these processes help to ensure a degree of correspondence between common influenza strains infecting the population and the strains used in the season's vaccine.
This is critical to vaccine efficacy with the constant introduction of new strains.
The research question was, what is the effect of correspondence between strains of prevalent influenza and strains included in the vaccine on the effectiveness of the flu vaccine in 10 flu seasons from 2010 to 2020? And right here shows how flu strains are structured.
The hypothesis stated that if the influenza strains used in the vaccine strongly correspond to the common strains infecting the population in a particular season, then the numbers of those infected, hospitalized, and killed by the flu will be decreased because vaccines containing virus strains similar to the influenza viruses circulating most commonly that season are increasingly effective.
Our experimental design was structured through the online accessible CDC annual flu reports.
The reports produced flu burden data regarding the numbers of people hospitalized, requiring doctor visits, and flu-related mortality.
The reports also produced data regarding common influenza strains infecting the population, as well as the 3 influenza strains included in each season's trivalent, meaning 3-strain, vaccine. Using this data, we produced a Microsoft Excel table which displayed the 3 most commonly circulating influenza strains and the 3 influenza vaccine strains for each annual flu season we analyzed. So the rows that are green across means that a common strain in a certain vaccine season correlated with a vaccine strain. And then the yellow rows meant that there was a common strain that did not correlate with the vaccine strain for that particular season.
Approximate correspondence of strains calculated by examining how many out of 3 strains included in a trivalent vaccine corresponded to the 3 most commonly circulating flu strains that season.
Our materials and methods correlate with the experimental design. So primarily we had the 10 CDC annual flu reports, 1 per season, which we downloaded from the internet. And with these annual flu reports, we derived the common influenza strains infecting the population, which we evaluated and recorded on a Microsoft Excel spreadsheet. Then the influenza strains included in that season's vaccine were evaluated and recorded on a Microsoft Excel spreadsheet. Then the data regarding the number of people hospitalized, requiring doctor visits, and flu-related mortality were also recorded on a Microsoft Excel spreadsheet. And from here, as explained previously, the correspondence between prevalent and vaccine influenza strains was calculated.
This summative data table displays the effect of correspondence between circulating and vaccine influenza strains on flu burden estimates.
Just by looking at this data, we can notice that flu seasons with a higher correspondence of strains have decreased burden estimates.
For instance, flu season 2011 to 2012 had 100% correspondence of strains and had 4.3 million medical visits, 140,000 hospitalizations, and 12,000 deaths.
whereas flu season 2017 to 2018 only had a 33% correspondence, meaning that only 1 out of the 3 vaccine strains matched to one of the 3 most commonly circulating flu strains that season. And we can see that there were approximately 21 million medical visits, 810,000 hospitalizations, and 61,000 deaths.
This shows a dramatic increase in the flu burden estimates evaluated within a season with much lower correspondence of strains.
Figure 2 represents the correlation between influenza-related medical visits and strain correspondence. The R value derived from this graph, which was negative 6.99, which is not necessarily as strong as possible, but it still indicates a negative correlation between influenza medical visits and strain correspondence.
Meaning that as strain correspondence increases, the number of medical visits tends to decrease.
This trend was also seen in the regressing line of best fit.
Figure 3 represents the correlation between influenza-related hospitalizations and strain correspondence.
The R value derived from this graph was negative 0.872, which indicated a strong negative correlation, meaning that as strain correspondence increased, flu-related hospitalizations tended to decrease.
This trend was also demonstrated in the regressing line of best fit.
Figure 4 represents the correlation between influenza-related deaths and strain correspondence.
The R value derived from this graph was negative 0.752, which was relatively strong negative correlation between flu-related deaths and strain correspondence.
Like the previous 2 graphs, the regressing line of best fit indicated a negative correlation between variables.
As discussed with each of the graphs, all 3 R values collectively demonstrated a negative correlation between correspondence of strains and flu burden estimates.
Therefore, the null hypothesis was rejected as the data demonstrated a negative correlation.
These conclusions collaborate with the overall strong negative correlation conveyed by the R values.
Therefore, the hypothesis is supported by the results, as the higher correspondence between prevalent influenza and vaccine strains resulted in decreased flu burden estimates.
These results concur with research that discusses ability to increase efficacy of seasonal influenza vaccines by corresponding a circulating strain to a strain contained in the vaccine.
This project could have been improved by the inclusion of quadrivalent vaccine data, as quadrivalent or 4-strain vaccination is used in many countries around the world and now is starting to be used more commonly in the United States.
This could have further tested the consistency of the correlation and enumerated any effect of the correlation that was altered by the type of vaccination.
Possibly the best way the study could have been improved would have been by conducting more trials, considering the publicly accessible flu season data recorded since the late 20th century.
A future study could examine flu vaccine efficacy during COVID-19 pandemic to see how COVID may affect levels of flu burden or vaccine effectiveness, especially since the addition of circulating COVID-19 virus may increase the difficulty to isolate prevalent flu viruses also circulating among the population.
We thank you for your time, and please inform us of any questions you may have.